Hey everyone, this is Mohammed Nadeem and welcome to my YouTube channel. Today in this video, we will take the in-depth intuition of Ampere law and we will also derive the expression for Ampere's law. So let's start the lecture from the basic. So here in the previous lecture, we know that if we provide the potential difference to a conductor, the current will start through that conductor, which produce the magnetic field around itself. And this is the magnetic field around this current carrying conductor, and it have different radius. And we know that this internal circle will have more magnetic induction, and here the magnetic induction will be less, and here the magnetic induction will be uh, less as compared to these two. Here we have that same current carrying conductor, and this is the diameter of the conductor, and this conductor is actually from your screen towards you, and the current in this conductor is electronic current, and that electronic current in the conductor is moving towards you from the screen. And if you put your left hand in the direction of electronic current, your curl finger will represent the magnetic field around the conductor. So if I take this loop and we extend this in each and every position of the magnetic field of this conductor, then it will show the magnetic induction at each and every position as a function of displacement. So here is the graph. I'm going to decrease this loop. So here this loop is toward the towards this conductor. So here the strength of magnetic field will be more. Therefore, this magnetic induction will be high near to this conductor. So here this is the magnetic induction, and this side is the distance from this conductor. So if I increase this circle, then the radius will be increased, and therefore the magnetic induction will be decreasing. So here this magnetic induction is decreasing. This is because when the radius is increased, then the magnetic induction will be decreased, as I have discussed in the previous simulation. And similarly, if we decrease the radius of the circle, then the magnetic induction will be increased. So here the magnetic induction is increasing. So here again the same simulation. First we take the conductor. This conductor is actually moving towards you from the screen, and there will be large number of magnetic field lines originating from this conductor in the form of circle, and each circle will have some radius. If the radius is increased, the magnetic induction will be decreased. So if we take the four conductor that is moving towards you from your screen, then what will happen to that magnetic field line? So that magnetic field lines will be added at each and every position around these conductor, and that addition will be the vector addition. Their magnitude and direction will be added. If we have large number of infinite number of that current carrying conductor which is moving towards you from your screen, then their magnetic field lines will be added in this way. So if I take the loop of that current carrying conductor, so it here this is moving uh, uh, away from you to your screen, and this is from your screen to you. So it will form a loop like shape, and here is the arrangement of the magnetic field around that. And similarly, if we take the solenoid, this is the one side of the solenoid have the large number of conductor in which the magnetic field. So here this the this conductor is moving towards you from your screen, and here is the large number of the conductors, and that all conductors are moving from your screen towards you. And similarly, there is a large number of the conductors that is moving from you to your screen. And here is the arrangement of the magnetic field lines around this, so it will make the solenoid like shape, and we will discuss this in the next video. So up to here, we master the concept of the magnetic field lines, the magnetic field around the current carrying conductor. And if that conductor is one, and that is two or four, or it make a sheet, or it make a solenoid like shape, or it make a loop, we this magnetic field lines will be different for each scenario. Here we have one conductor, and we know that around this conductor there will be the magnetic field lines, and that magnetic field lines will make a circle like shape. So here this is the one circle, and this is the other circle, and there will be large number of the circles which is made by the magnetic field around the conductor, and that circle will extend it to the region in which the effect of this conductor is present. So here we have large number of the circle around this conductor. Okay, and here inside this conductor the current is flowing. So here this is the direction of the current, this is the direction of the conventional current, and put your the thumb up your right hand in this direction, so your curled finger will be in this direction around this conductor. So this around this conductor, it will give you the magnetic field around the conductor in the form of circles. So now in order to derive the Ampere's law, so we take the Amperian loop. Okay, so here I'm going to take the Amperian loop. Okay, I'm taking the Amperian loop here. So this Amperian loop is actually, we select some circle inside the magnetic field around this current carrying conductor. Okay, here this red color is the Amperian loop. Now the question is arise here is that, as we call the circle which is made by this magnetic field around this current carrying conductor as an Amperian loop, I am talking about these lines. So this is the circle, and we have this is the circle. So my question is that, can we call this circle as Amperian loop? Amperian loop. Or can we call this circle is Amperian loop? So my answer is no. Here we have the conductor, okay, and the current is flowing in that conductor. It will produce such like shapes, such like circle in the form of magnetic field. So here this was the one case in which the current was flowing in the conductor. Now, if I increase the current for the same scenario, then these lines will be moved toward this conductor. Okay, and mean that these circles will be moving near to each other. Now, this Amperian loop will be displaced, and we know that the Amperian loop must be fixed. That is not change with the change in the current in the conductor. Okay, so we will. This was the concept of the Amperian loop, and here this Amperian loop is actually the imaginary circle. So here this Amperian loop is actually the imaginary circle in the magnetic field around the conductor. Okay, we can take this imaginary circle of the different radius. So here I can increase the radius. So this is the radius. So this is also the Amperian loop inside the magnetic field around the current carrying conductor. Okay, so here we select the Amperian loop, and now we will uh, apply the mathematics, and through this Amperian loop we will find the current in the conductor from this magnetic field. Let's derive the expression for the Amperian loop. We have that same scenario. This was the conductor. The current was flowing in that conductor. And here we take the Amperian loop around this current carrying conductor. So this is the Amperian loop with this pink color. And this is the conductor. Okay. According to Ampere, you will have to divide the whole circle. As you consider as Amperian loop, you will have divide that whole circle into small parts. So this is the one part of the circle, this is the other part, and this is the other part, and you will have to divide that into in large number of parts. And we know that here we have the current carrying conductor, and this Amperian loop is present at the radius r from this conductor, and there will be some magnetic induction present here in this circle. So we have the magnetic induction B here, and also on this part of the Amperian loop. Okay, this is the magnetic induction in here, also the magnetic induction in here, also the magnetic induction, and for each and every part of the Amperian loop there will be some magnetic induction. Okay, and this part of the Amperian loop is del L, this part of the Amperian loop is del L, this part of the Amperian loop is del L, and similarly, so if we take large number of these parts, so this is del L1, del L2, del L3, and del L4, and similarly we will take these up to del Ln. Okay, we will take that up to del Ln. And for each del n, there will be magnetic induction. Okay. So why we divide the whole Amperian loop into small parts? Because we are interesting to have the direction of magnetic induction, and the direction of the length is same. So here the direction of this magnetic induction and this del L is the same. According to in pair, we will take the dot product of all these points of the dot product of this magnetic induction and this del L at each and every part of the circle. So here we will take B dot del L1 plus B dot del L2 plus B dot del L3 plus up to B dot del L N. So we will take the dot product of magnetic induction and del L at each and every part of the Amperian loop, and we will add that. According to the Ampere, if you add this, it will be equal to the mu naught times of the current enclosed by that Amperian loop. So current enclosed and closed. Here he said that he stated that if you take the dot product of magnetic induction and del L at each and every position of the Amperian loop, and if you add that, it will give you the current enclosed by the conductor present inside that Amperian loop. So here we have to determine. So let's say this is the equation 1. So we are going to determine the expression for B. So B is a vector quantity. We will put the this arrow and that B. So here B is actually this magnet. B is the strength of the magnetic field, and this Amperian, this part of the Amperian loop. So this magnetic induction, as we discussed in the previous simulation, is inversely proportional to the radius of that circles, which is made by the current carrying conductors. And this B, the magnitude of this B, is also increased by increasing the current in the conductor. So here B is directly proportional to I, the current of the conductor, and inversely proportional to the radius. And if we instead of this proportionality sign, we will put the equal sign and the constant. Okay, and this is the I and divided by the radius. So instead of this constant, we will put mu naught by 2 pi. Okay, then this equation become, B. Okay, um, B is equal to, instead of this constant, we will put mu naught by 2 pi. Okay, and this I divided by R comes in its own position. This is the equation 2. If we add del L1, del L2, del L3, del L4, del L5 up to del Ln, it will give us this circle, and the circumference of the circle is 2 pi r. So this is equation 2. So here I am going to write it. So let's say we have, okay, we have del L1, okay, this one, plus del L2 plus del L3 up to del Ln. Okay, if we add all these part of this Amperian loop, it will give the circumference of this circle, and the circumference of the circle is equal to 2 pi r. Now multiply equation 2 and 3, which implies that the left side of equation 2 is B. So B, which is B, and the left side of the equation 3 is B dot del L1, okay, plus so, and the left side of the equation 3 is the summation of del L. So here we have del L, we can write summation here. And the right side of the equation 2, now instead of B, we will put mu naught by 2 pi. Okay, and here we have the I, and here we have the radius R. And the right side of this the right side of equation 3 is 2 pi r. Now this 2 pi r and this 2 pi r will be cancelled. So here this equation become the summation of the magnetic induction dot the small length, and which is equal to here mu naught time I. So this is the expression for the Amperian loop. Here is actually we have the conductor, and around this conductor there will be some magnetic field, and inside that magnetic field we consider the Amperian loop, and we divide that Amperian loop into small pieces, into small lengths. So that length is del L1, del L2, del L3, del L4, del L5, and if we add that all del L's, then it will become the circumference of the circle, and here this is the circumference of the circle is equal to 2 pi r. And here at each part of the circle around this conductor, there will be some magnetic induction, and that magnetic induction is directly proportional to the current of the conductor and inversely proportional to the radius of the loop around this conductor. So here is that expression. It is directly proportional to the current and inversely proportional to the radius. And if we put the constant here is mu naught by 2 pi, then it will give us this expression. So now according to Ampere, if you multiply this the B and dot dl at each and every position, and you sum that, it will give you the 2 pi 2 it will give you the mu naught I. So we follow the instruction of the Ampere, and here we take the dot product of the magnetic induction and del L at each and every part of the Amperian loop, and then we will add that. So here this B is equal to mu naught I by 2 pi r, and this del L is equal to 2 pi r. So this 2 pi r and this 2 pi r is cancelled. So here is the summation of B dot del L is equal to mu naught I. Okay, so it means that the summation of the product of the magnetic induction with the del L is equal to mu naught time of the current enclosed. So here this mu naught is the permeability of the medium. So this is the permeability ability of the medium, and this is actually the ability of the medium to permit the magnetic field. So in this is for the space, so this is for the vacuum, and for the uh, other medium we will put the permeability of that medium here. And from here if you have only this B, okay, the magnetic field around the conductor, then you can find the current through that conductor. Or if you have the current in the conductor, then you can find the magnetic field from this expression. So here is that same scenario. We consider the Amperian loop around this current carrying conductor, and according to the instruction of the Ampere, we derive the expression for this. So here in this simulation is also that. So we have the summation here is used as integration. So the integration of the magnetic induction at a point and the dot product of that with the dl will give you the mu naught time of the I. Okay, and here is the this expression. It will be equal to mu naught time I enclosed, and this is the expression for the B. B is equal to mu naught I by 2 by r. This B is depend upon this I, and it depend upon this r, and mu naught by 2 pi is the constant here. And from here we have only the current, okay, and we don't know about the magnetic field. So here we can find the magnetic field as the B is equal to mu naught, the value of mu naught is constant, and here I is we have the I is the current in the conductor. We know that, and similarly 2 pi is the constant, and R we can find from the loop of the Amperian loop, and from this we can find the magnetic field around that conductor.